All right, hi everybody. I'll give it a second to make sure it's actually working and then we'll get started. What do you think? Nothing yet? Okay. Okay, cool. I'll turn it back on to. All right, so we're good. All right, so today we're going to be talking about energy and calorimetry. So energy, we'll talk about what that is, and then calorimetry is measuring the amount of energy that either is contained by something or as a result of some sort of process that transfers energy. It's really measuring heat, which is a way of transferring energy. All right, so first, anyway, let's define energy. The technical definition, oh no, what's happening here? Why is this? It's not showing up. Hold on. Oh, there it goes. Okay. Good. Where do you see my writing? There it goes. Okay. Energy is officially defined as the capacity to do work. So what is work? Well, in physics, the definition there would be work is a force applied over a distance, so like lifting something up or pushing something or whatever. And there's lots of different ways you can think about that, pushing something up a hill or whatever. And energy is the capacity to do that. So we think about energy in different ways. Sometimes we think about the kinetic energy, the energy of motion, the potential energy that something has, the stored energy. In chemistry, potential energy is really important because that's like our chemical energy, the energy stored in chemical bonds. And so particularly what we're interested in is the idea of a fuel, what makes something a fuel, and then how do we measure whether or not it's an effective fuel. And that's what we're going to do with our biodiesel that we made. We're going to see how much energy is in those actual stored bonds by doing an experiment. So how do we measure energy? Well, there's lots of different ways of thinking about energy, the ways that people have thought about energy over time. So there's lots of different units for energy. So the first one we're going to look at is the calorie. This is maybe the easiest for us to understand. 1 calorie, and it's important to have a lowercase c, which we'll talk about why in a second, is the amount of energy it takes to raise 1 gram of water 1 degree C. So if you have 1 gram of water, which would also be 1 milliliter, so think about like in the graduated cylinder, 1 milliliter of water, and you want to raise it 1 degree C, so from 25 degrees to 26 degrees, that's 1 calorie of energy. So if you wanted to raise, let's say 10 grams of water, 1 degree C, that would be 10 calories. If you wanted to raise 10 grams of water, 10 degrees C, that would be 100 calories. So hopefully you can start to see this pattern a little bit, that if we want to raise a certain amount of water by a certain amount of degrees, we can simply multiply those together. So we might write the calories to heat some water is the mass of water in grams times the degrees that we want to raise that mass of water. So if we have 10 grams of water, we want to raise it 5 degrees C. That means it takes 1 calorie to raise each gram 1 degree, so that's 10 times 5 would be 50 calories. All right. So complicating this a little bit is that a capital C calorie, so a calorie with a capital C, is actually 1,000 of the little c calories, which is more correctly referred to as I guess, I don't know about correctly, but more helpfully, clearly referred to as a kilocalorie or a kcal. But this is the calorie that's on food. So if you look at food and you see that, it has a certain number of calories in it, that's actually the big C calories. So if you have 1 calorie of food, 1 big C calorie of food, that's enough energy to raise a gram of water 1,000 degrees. Not really because um, it would boil, but let's go the other way. Let's say 1,000 grams of water, a liter of water, 1 degree. So one food calorie contains enough energy inside it to raise this water by that much. And this is how the technique of calorimetry works, where we heat something, or we burn something, sorry, not heat something, we burn something that is releasing the chemical energy, and then we can use that to heat water, and we can figure out how much energy was in there by the amount of temperature that the temperature change that the water experiences. And we're going to do this next week with some food, and then we're also going to do it the week after with the biodiesel. So a couple notes about that experiment, about those experiments, and we'll talk about this more when we get to the food next week too. So the food, you can burn it, you can release all that energy, and you can measure how much energy is released. But that's not always necessarily correlated to like the energy that it's used for in the body. So when you eat food and you get some energy from that food, it's not always necessarily related to the actual calorie count that you would measure in the lab, because our body isn't burning the food in the same way when we like literally light it on fire and combust it. To give you a sense of what that looks like, if you have some food, let's say it is, it could be made of whatever, but let's say it's like CXHYOZ, meaning it has some amount of carbon, hydrogen, and oxygen. What we're doing when we're burning it or combusting it is we're reacting it with oxygen gas, and that's producing carbon dioxide and water vapor. So that's a chemical reaction. It's not necessarily balanced in this case, but if we had actual numbers here, we could balance that equation. And if we react it with enough oxygen, we should be able to convert all of this substance, whatever this might be, into carbon dioxide and water. So in a full correct calorimetry experiment, there's nothing left over afterwards. It's all been converted to carbon dioxide and water. In our bodies, it doesn't quite work that way. We're not just reacting our food with oxygen and creating carbon dioxide and water. We're going through all of these enzymes and various processes to use the food. So even though we kind of take these ideas of calories on labels and calorie counts to be accurate, there's actually really a lot of variation there. And the way that we metabolize different types of food and whether or not that turns into energy or is stored or is excreted or whatever, there's a lot of just variation person to person. So that original idea of like we're going to measure the calories through calorimetry, and then that's going to tell us something about the actual energy content of the food, is not always as simple as that sounds. It doesn't quite work like that. So keep that in mind next time you think about calories of food, that your body is not really, it's just because something has 100 calories and something else has 200 calories, doesn't mean that that other thing has 200 or has 100 more energy units that you can use necessarily. You might be processing those things very differently. All right, let's look at a couple other units of calories, and then we'll talk about heat capacity. Units of energy, and then we'll talk about heat capacity. So some other units, the official SI unit of measure of energy is the joule. So the joule is smaller than a calorie. 1 calorie is about 4.1, I think 9 joules. And that's a little c calorie. So you might often see, or you might see things, energy measured in joules or kilojoules. That's another measure of energy. A somewhat common one in this country is the British thermal unit, or BTU. I don't have the number offhand, the conversion between calories and BTUs. You can look it up, but this is still used a lot in heating and cooling. So you might have a furnace that's rated in a certain number of BTUs, or an air conditioner or something like that, or a heater, a space heater. Stoves and ovens are sometimes, gas stoves and ovens are sometimes rated in BTUs. BTU is actually comparable to the calorie in that a calorie is a certain amount of water in grams, or it's the amount of energy it takes to raise a gram of water 1 degree C. And I think a BTU is the amount of energy it takes to raise a pound of water 1 degree F. So it's like the English or imperial units version of the calorie. And there are some other ones as well. We won't probably use as much in this class. The kilowatt hour, kWh. This is used to, like on your electric bill or your energy bill in your house, would be measured in kilowatt hours. So a watt is not a measure of energy, it's a measure of power, which is energy over time. So in order to get from watts back to energy, you have to multiply it by the amount of time. So if you have a 60-watt light bulb, that means that it uses a certain amount of energy over the time that it's lit, and the longer it's lit, the more energy it's going to use. So if you use a 60-watt light bulb for an hour, you've used 1 watt-hour of energy. So that's still in use for homes. If you're like looking at electric vehicles and things like that, or those are often, the battery capacities are often measured in kilowatt hours, because it can be proportional to how it's used, because as you, like, depending on how you drive or how you're using that device, you're using more or fewer watts as you're doing it. All right, so that's units, and we will mostly use calories in this class. But one thing we're going to see in 2 weeks is when we look at the biodiesel project, we want to compare the biodiesel properties to other types of fuels. And sometimes when we look up the values for those other types of fuels, they're in these other units. So we might have to do some conversions back and forth to make that make sense. Okay. So the last thing we want to talk about with energy today is heat capacity, which is related to, very similar to a quantity called specific heat. So the heat capacity is sort of like the opposite of the calorie definition. It's the amount of energy it takes to heat 1 gram of a substance 1 degree C. So for water, the heat capacity is 1 because it takes 1 calorie to heat a gram of a substance 1 degree C. And so we get kind of a weird unit from that. So for water, the heat capacity is, which is actually just a capital C is what that's usually referred to as. It's 1 calorie per gram degree C. So that's saying it takes 1 calorie to heat 1 gram of this substance 1 degree C. But other substances have different heat capacities. So as an example, think about, if you're outside in the summer, maybe you've got like a bottle of water in your car. If you're out in the bright sun in the middle of summer, what gets hotter? The car, like the surface of the car, or the water that's in the car? It's probably the surface of the car, right? And that's because metals generally have a much lower heat capacity So for example, this is where we have to do some conversions here because most heat capacities are often given in joules instead of calories. But here's some calorie ones maybe. No, this one's in joules too. So just to compare, we said about 4.18. So the heat capacity for water is 4.184 joules per gram degree C. And then if we compare that to iron, like the main component of steel, is 0.449 joules per gram degree C. Right, so a tiny fraction of that. And what that means is it takes about almost 10 times the amount of energy to heat water 1 degree than it does to heat iron. If we look at something like copper is even lower, 0.385, and aluminum 0.903. So what kinds of things then have higher heat capacities than water? Well, gases for one. So gases could have higher heat capacities, meaning it takes more energy to heat them up than it would for water. Actually, ice and steam actually have lower heat capacities than water, so it's easier to heat up ice and steam. It takes less energy than it does for water. So the actual equation for measuring heat, which we're going to use for our calorimetry next week, Q, which is heat. I know it's a weird unit or a weird variable for that, but that's what's used. So the heat is equal to M, and we'll talk about each of these, M times C times delta T. So M is the mass of whatever's heated. So the thing that the heat goes into. So in our cases, for the calorimetry experiment, what we do is we burn this thing and we use that heat to heat up water. So then M is the mass of water in this case. Then the C is the heat capacity. So again, if we're heating up water, we're going to use the heat capacity of water, which is 1. And then this delta T is the change in temperature. So not the absolute temperature, because it doesn't matter what actual temperature it is. It's the change in temperature. So if the water started at 25 degrees and then we burned the thing and it heated the water up to 28 degrees, then that would be 3. Right? So that the change in temperature would be 3. And then this is why this equation kind of reduces down to what we wrote earlier up here, mass of water times the degree C, because the heat capacity of water is 1, so we can sort of functionally ignore that in our calculation. So then we have the mass of water and then how much the temperature has changed through that heating. All right, so for example, if we heat 100 grams of water from 22 degrees C to 30 degrees C, how much heat was transferred? So we would say the heat, Q, is the mass of water, which is 100 grams, times the heat capacity of water, which is 1 calorie per gram degree C, times the change in temperature, which would be 30 minus 22, which is 8. So 100 times 1 times 8 is 800, and the final unit there is calories. So the grams and the degrees C cancel, and we end up with little c calories. So it took 800 little c calories to make that change. All right, so when we do this next week, we'll be doing this with food, with your own design of calorimeters. And then the week after that, we'll do it with the biodiesel with the actual like lab equipment calorimeters, so that you can see kind of the difference in the setup and how that all works. So to prepare for lab next week, please look up a little bit about calorimetry, and in the instructions there's some like practice problems kind of like this of doing some calculations with calorimetry, so it might help if you look over that stuff and think about how you might set up a calorimetry experiment before we do it next week. All right, let me check, make sure there are questions in the chat. Looks like no. You got anything? All right, then see you all next week.